Yeah, hi, good evening, everyone. So, welcome to the week 9 open session. Can anyone confirm am I audible properly?
Yes, sir.
Okay,
You're
fine.
audible.
Yeah, okay. So, in week 9, I hope you watched the video, week 9 content. Anyone? Bikram Singh, okay. Okay, fine. So week 9 basically we are learning the dynamic programming approach. So what is this dynamic programming and how, when we can use this dynamic programming and how we sometimes that greedy algorithms actually doesn't work for some problems, so we can use this dynamic programming approach to solve, and how we can reduce the operations by just solve the problems in some uh, cleverly. Okay, so we will just discuss the topics related to dynamic programming, and we will just discuss all the things which are discussed in the week 9, all the algorithms. So those are standard algorithms. Okay, so let me share my screen. If anyone have any query before that, then you can also ask. I i hope my screen is visible.
Yes.
So, in week 9, these are the topics which are discussed. So, there are some problems: a grid path, longest common subword problem, longest common subsequence, array distance, matrix multiplications. So, these are very common problems which are solved by this dynamic programming approach. Otherwise, there are lots of problems can be solved using this dynamic programming approach. So, first we will discuss. So, what is dynamic programming? Okay, so, according to the dynamic programming approach, if any problems can be solved by a sub-problem solution. So, like if any problems contains the two property, that overlapping sub-problems and optimal substructure property. So, these are basically two property. So, overlapping sub-problems means if we just select the smaller part of the problems. Okay, so our main goal is to solve the larger problem, but if we select the sub problems of that larger problem, and if we solve that first, and we use the solution of that problem to solve the main problem, so that is the overlapping sub problem property. So that means our main problem solution is dependent on the sub problems solution. So this property, and other property is this optimal substructure property. So that property is, said that if we can achieve the optimal solution by solve this sub problem solution. Okay, we are solving sub problem, and after getting the solution of sub problems, we can achieve the optimal solution for the main problems. Okay, so this is the property of optimal substructure property. So if any problems contains these two types of property, then we can think about the dynamic programming approach to solve that problem. So here one example is given. So this example is very popular, and you all know this problem. So this is the yeah, Fibonacci series. Okay, so I hope yeah, or we can say that the problem is the nth number in the Fibonacci series. What is the nth term in the Fibonacci series?
Fibonacci.
Okay, yeah, Fibonacci series. So there are some multiple way to solve this problem. So first we will look about the this recursive problem. Okay, recursive solution. So I hope you have already seen this solution in the initial of this course, when we are asking the complexity for this type of solution of Fibonacci series. Okay, so you can see the solution. What we are doing, we are just writing the recursive solution here. So this is the recursive solution, and inside this first is the base condition. Okay, in the every recursive solution, we write the base condition, and another part is the recursive call part. So every time we just reduce the problem, so that we just call recursively. Okay, and that recursive call will reach at the base case after some time, after some calling. Okay, and at that time we will stop the recursive call. So this first is the base case, so we will stop the recursive call process when we reach this at this condition. Otherwise, always we will just call the recursive part on this f fib rec on n minus 1 and n minus 2. So we are passing this input. Initially we are getting this n, and inside this we are passing this n minus 1 and n minus 2. So you can see in the solution we are reducing the value of n, okay, n minus 1 and n minus 2 in that way. And after some time we will reach this condition if n is less than equal to 1. So if when we will reach this condition, we will simply return the value. Okay, we are not calling recursively again. So this is the recursive function for this nth term of Fibonacci series. So if we draw this logical structure for this recursive function, so this is the recursive this logical structure of calling the function. Okay, so initially we are calling the this fib recursive on the value of 5, n equal to 5. Okay, after that, so this value is not equal to or less than 1, so this is not satisfying the base case. That means we are calling n minus 1. So okay, n minus 1 means 5 minus 1, 4. Same time, so this is the first part, okay, of the call, and second part, this is the this side, okay, n minus 2. So 5 minus 2 is 3. So this is the second call. So now this is the separate problem. Okay, this is the sub problem of the main problem. Now once again this will be solved separately. So when this is the separate call of the function when we are passing n equal to 4, and next time this will be called again on n minus 1 and n minus 3. So this n minus 1 part is this fib 3 and fib 2. Okay, same. Once again this is the separate part. So fib 2, fib 1, and fib 1, fib 0. So these are the base case, okay, when value of n is 1 or 0, and we are returning directly n. Similarly, this one is the separate part of the calling fib 2, and we are passing n minus 1, 1 and 0. Similarly, for this side, if you look this fib 3, n equal to 3 we are passing, now 3 n minus 1 and n minus 2. So this will be the call of the fib 3 part. So this problem is actually expand in that in this tree manner to bottom. So here you can see we are solving the same problem multiple times. So if you see in this logical structure, so this fib 1 and fib 0, this is repeated many times. Okay, so fib 1, this is also here. Okay, fib 0, this is also here. Same, fib 1 is repeated here. So so that means we are calling this function when we are passing n equal to 1. So this function we are calling many times in this okay, recursive structure. Same, fib 2 we have called one time here. Same, this is repeated here, this is repeated here. Okay, so that means that sub problems is repeated many times in this recursive call structure. So fib 3 is repeated here and repeated here. Okay, and this same fib 1, okay, this is repeated multiple times. So how we can, when we are solving this fib 1 and fib 0 and fib 2 one time, so why are we are solving again multiple times in this recursive structure? Okay, so this is just a repetition of the same operation. If we have already solved this one function, why we are solving the same things again? And if we merge the solution of these sub problem, we are getting the final solution of the main problem. So how we can reduce this additional operations which we have already done one time? So why we are repeating multiple times these things? So can we ignore this? Can we just improve this? Okay, by some logic? So this is the approach of the memoization here. We are just using one memo. Okay, so this is for just a memory memorization. Okay, so we are just want to store some result of the sub problems, and if that problems comes again into the process, then we will directly read the result of the previous solution. Okay, we will not solve again. Okay, if any main problem is divided like this, so this is the p and this is p1, p2, p3. Okay, and this is the p4 and p like this is repeated like p1 and p2. Okay, so if we have solved this like p1, here and P2 here, then we will no need to solve this part again here. So P1 is, we have already solved this problem, sub problem here, so we will directly use the solution uh, from this which we have already solved. Okay, same for the P2 we have already solved here. Then we will not solve again this problem, sub problem, and we will directly use the solution of the previous computation. So same things we want to do in this memoization techniques. Okay, this is one approach of the dynamic programming. Okay, this first one is the simple recursive function. This is not a dynamic programming, this is the dynamic programming. So what we are doing, we are storing the uh, this memoization using the dictionary. Okay, if you see the problem logical structure of the calling, now same method we are using, but what we are doing, we are just maintaining some memory, and we can say that this is a dictionary. Okay, so at the time, so this is the recursive call things. Okay, so we will just come at this position at this time, this is the base case, we will directly return the solution from here. So once fib1, this value is reaching at the base case, we will directly return 1 from this side. And when we are just getting the final solution of this call, we will also store that solution in our dictionary. Okay, so when our k value, so here we are just assuming that this k is the this input value of the function. If k value is 1, we will directly store in our table 1, 0, 0. Okay, so this is the base case which we have mentioned in our solution. So this is representing the base case. You can see if n is less than equal to 1. Okay, so if this is 1 or 0, so we are directly returning n, and we are storing this result into our dictionary. Okay, if n equal to 0, output is 0. If n equal to 1, output is 1. So by default, this is the base case. But what happened now? So this fib0 and this part we have directly getting from the base case, and we are also storing this value into our dictionary. And we are computing this fib0 and fib1 by this fib2. And after sum of this side we are getting 1, this side we are getting 0, and we are adding of both the value 1 and 0, and we are getting here fib2 value equal to 1. So that result we are also storing into dictionary fib2. Okay, so first time we have solved this, we have stored the result of here. Same, this is a base case, this will return 1, and this side we are getting 1, so 1 plus 1 we are getting 2 here. So fib3 we are storing 2 result here. Okay, in the dictionary, because this value we are computing first time in our process. Okay, now we will just move back, and there is one part from here, so we will solve this. So fib2, you can see that this is the repeated call fib2, which is we have already solved, and we have stored that result into in our memory. So 2, what is the result when k equal to 2? So this result we will directly access from the dictionary, and we will directly return the 1 value from here. We are not exploring again. So this like fib1 and fib0 like this. We will look in our memory, and we will check if this solution is already available in our dictionary. We will directly read the solution. So from here we will directly return the answer 1 to the top above side. Okay, so this part we are getting 2, and this part 1, so plus we are getting 3. So fib4, this is now solved first time, and we will store in our dictionary 3. Repeat similarly when we are just going back to the top, so the left part is completed. Now this part we will look the second call, what is the solution for fib3. Now we have already solved this fib3 previously, so we will directly read the solution 2 from here, and then 2 value will be returned to the above call. So 3 plus 2 is equal to 5. So 5, this will be the answer. Okay, so now you can see that here there are many calls we have saved. Similarly, we have reduced 2 call from here, we have reduced 2 call from here. Okay, so in this way you can just see the changes of the structure. So how many calls we have reduced if we are using the memory, if we are storing the solution of the sub problems in our memory, and we are directly using the solution if that part is repeated again. Okay, so this is called the memoization, and here we are also using this recursive approach. Okay, so this is a recursive approach, we are calling the same function again. So this is also a overhead, we are using the recursive things. Can we solve this problem without recursion. Okay. So next approach is dynamic programming approach. So this is the okay. So this one is called as a top-down approach. Okay, top-down approach, and this is called as a bottom-up approach. So here we are starting from the sub problems and we are we are moving to the top. Okay, we are starting from the sub problem like this. So we will start from always from this side. So this is a one sub problem and this is a one sub problem, and we will get the solution of the final main problem. Okay, but in the previous one we are starting from the top and we are just calling into the sub problem, and that after that we are solving from the bottom. So we are starting from the top down approach. So we are starting from top to bottom, then we are solving from bottom to top in this manner. So this approach is called top down approach. But this dynamic programming approach, here we are changing the strategy. We will use the same things. We will store the result of the sub problem and we will use that result into the to solve the remaining problem.
Excuse me, sir.
Yes.
Sir, isn't memoization a type of dynamic programming?
Yeah, that is also a type of dynamic programming, and that is called as a top-down approach. But most of the time, we actually not use this recursive recursive call things in the dynamic programming.
Sir, but now we have something separately called as dynamic programming, although memoization was a type of dynamic programming.
Actually, this is the main things. Actually, here we are not using this recursive call part. Okay. But this is also come under the dynamic programming things. Okay, but we are reducing more effort in the next approach.
Okay, sir.
Yeah, so this is the two category actually in comes under the dynamic programming things, top down and bottom up approach. But we always try to just reduce this recursive things also in the dynamic programming. Okay, so here you can see, so dynamic programming, this is the bottom up approach. So here we will pick the sub problem directly. Okay, we are not using the recursive call. So we are not starting from the main problem and then we are just going to the sub problems. Then we are just achieving the solution. Here we will directly pick the sub problems and then we will solve the sub problem first. Then we will combine the solution of the previous sub problems and then we will get the final solution. So here you can see that we are just starting from fifth n. So suppose if n equal to 5, so what will be the output? So what we are doing, we know that if what is the base case we have taken in the previous example, if n equal to 0, output is 1. Okay, no, sorry, 0. Okay, if n equal to 1, output is 1. So this two steps we know. What are the zeroth term of the Fibonacci series? 0. What is the first term of the Fibonacci series? That 1. What is the next term of the Fibonacci series? So we can compute the next term always by adding the previous two terms in the Fibonacci series. Okay, so 0 plus 1, this will come 2. Okay, so that means we are adding this and this here. Okay, next term we will add two previous terms. So next this one and this one. Okay, so we will get 1 plus 2, 3. So I think I missed something. Okay, so this is 1. Let me just update this. Okay, so first term is 0, second term is 1. Okay, next term will be sum of previous two terms. So sum of previous two terms is 0 plus 1. Okay, so 0 and 1, we are getting 1 here. Okay, so this is the sum of previous two terms, and next terms will be calculated by the previous two sum of previous two value. So 1 plus 1, 2. Okay, so like this. So we will get 1 plus 1, 2 here. Next term, so same things, we will repeat the process. 1 plus 2, 3. In this manner, we are getting this Fibonacci series. So same things what we are doing in the problem. We are just starting from this part. So we know that fib1 is 1, fib0 is 0. What we will do, so this is the sub problem. Okay, so we are always starting from this sub problem fib0 and we are assigning this value. What is the solution for the fib0 and what is the solution for fib1? That is 1. Okay, this is 0. And after that, what we will do, we will just start from this fib2. So we will just read the previous two values. So what is the value of fib1 and what is the value of fib0? So we are directly reading the solution of previous two sub problems. okay, 1 and 0, and we are adding to get the solution for fib2, and here we are getting 1. Okay, for the next things, so fib3, so we will read the previous two subproblem solutions. So what is the solution for fib2 and fib1? Okay, which is already available in our memory or dictionary, something, some place, and we will directly access this solution in the constant operation from the dictionary. Okay, so we will read this solution from 1 here, and one value this here, so 1 plus 1, and we will get this solution for 2 here. Okay, so same manner, 2 plus 1, 3, we will get the solution, and finally 3 plus 2, 5 we will get. Okay, so this thing we are performing by simple iterative process. Okay, what we are starting, so initially we are maintaining one table, or we can say here we are just giving the name of table, and so like this, how many terms we need to finalize for this. So here n term. Okay, so we will just creating one list here, and all value are actually 0, and we are taking this value n plus 1. Okay, so 0 into n plus 1, that means 6 value, 0. After that, we are assigning that t1 equal to 1. So we are just changing this value. So we are maintaining, so this actually we are maintaining the like a solution of sub problem. So this is the solution for 0th term, this is the solution for first term. Okay, according to the index, we are getting this 0 and 1. Now after that, we are simply performing one loop from 2 to n plus 1. So this loop will run 2 to n. Okay, so 2, 3, 4, 5. Okay, and after that, what we will do, we are simply getting the solution by adding to previous solution from our table. So for this value, we are reading previous two value. What is the value of 0 index and 1 index? 0 plus 1, 1 we are getting. For this location, we are adding previous to 1 plus 1, 2. For this location, we are adding 2 plus 1, 3. Same 2 plus 3 equal to 5. And finally, we are returning Tn. So this is 5. So you can see that we are starting solve the problem from the sub problems first. Then we are getting the final solution by using the previous solution. Okay, so in this manner, what is the complexity of this is simple order of n. You can see this is the complexity of order of n. Here we are running one single loop 2 to n plus 1. So this loop is actually generating n complexity. Same things, we are creating one list of n size. So this is also an order of n operation, but both operations are separate. So overall complexity will be order of n. But what is the case of here? So similarly here we are also performing same n steps. You can see that this is the minimum possible path. Okay, so one calling path. Okay, so fib5 to fib1. After that we are getting solution, but still some are remaining recursive call is also there. So it will increase some cost compared to the final solution. And here complexity of this is also closer to order of n, but the cost is actually a little bit extra compared to this iterative solution. But this solution is actually totally 2 to the power n. Here we are performing this 5. So every time we are calling 2 times. So this tree will be expanded in that way. And in final levels, we have total number of steps 2 to the power n. Okay, so here 2 to the power 0 and 2 to the power 1, like this 2 to the power 2, and this is the last level will be the final nth level, so 2 to the power n. So this is the highest term of the order of n. So complexity will be bigger 2 to the power n, so which is very high compared to the dynamic solution. So in that way, we can solve the problems by using the sub-problem solution. So this is the way of the dynamic programming approach. But here actually to solve the dynamic programming problems, some practice is required. So this is not a fixed formula or fixed things to solve this problem. First, you have to figure out that how problem can be break and how you can use the sub-problem solution to get the final solution. So that things you have to figure out in the problem. So every problem is a new problem, and after solving some problems, some set of problems, you will figure out that how we can approach the dynamic programming. So here some practice is required. So this is the first problem, the example of dynamic programming. Next problem is discussed this.
Excuse me, sir, before that.
Mhm.
Sir, the dynamic programming code, could you?
Okay.
Sir, I'm not able to understand how this code is different from the one, the previous one. Before this, yes, this one.
This one.
Yes.
This is the recursive structure, and the calling structure we have mentioned here. You can see that this is the two recursive call in the each steps.
But sir, code-wise, it doesn't seem very different.
But complexity-wise, it is much. There is much different. If you see this code, we are starting from this call. This is a recursive call. Okay, so we have to figure out the recurrence relation for this. If you find out the recurrence relation for this, you will get like this t. What is the total steps are tn equal to, in every steps we are calling this two recursive call. So this is t n minus 1 and plus t n minus 2, and what are the remaining time is constant time. Okay, so big O 1 we can write this. Okay, so this is the recurrence relation for this. And if we draw the logical structure of the calling, okay, so we are getting this tree structure. Okay, so we are starting like this f5, and inside this function we have two call. Okay, every time we have two call. Okay, so because of that, two child is created. So f4 is created, f3 is created according to this value n minus 1, n minus 2. Inside this 2 will be created, same 2 will be created. So in that way, suppose if this n value equal to 10, so you can see that how many recursive call will be generated. So
Yes,
that
sir.
steps are actually very high compared to the normal iterative solution. So as we calculated, the complexity for this is 2 to the power n. Suppose if n equal to 10, so the total steps will be 2 to the power 10, 1024 approximately.
Yes, sir. Yes, sir. I understand.
Okay.
Yes.
So this is the recursive
It's
approach.
2 to the power 10 or 2 to the power of 10 minus 1? 2 to the power of n minus 1.
No, 2 to the power n. No? We generally use the highest term. Okay, so we are reaching at this last level. Still we have total steps here 2 to the power 0, 2 to the power 1, 2 to the power 2, like this, and we are reaching this last level. So this is the nth level. No? So this is the, if any value equal to 5, so you can see that 1, 2, 3, 4, 5 level we have. So this here we will get. Still, if you are getting to the 2 to the power n minus 1, so that will also be considered as a 2 to the power n. We can just ignore this constant. Okay. So this is the thing. This is the basic idea of the dynamic programming. Now we will just look some more problems. So how we can solve the other problems with the same approach. So next problem is discussed in the lecture is grid path. Okay, and what is the
So
problem?
can you please explain the structure at a block level? Each block, what is it really doing?
Block level means?
Means each blocks of this structure.
No, I'm not getting. You're talking
Like
about.
for example, row number 1 to 5, then it's a block. Then 7 to something going down.
Oh, you're talking about this grid path.
Yes.
Okay,
Not the
that.
grid, not the grid path. I'm talking about the code structure. How do we logically we really think about it before putting the code lines? Not
Okay,
the
so yeah, because of that, I am saying that for this dynamic programming approach, you need some practice. You cannot figure out the solution directly after solving the one problem or two problems.
That's
Okay,
fine. That's fine. But we have to start it somewhere, no? So that starting point only I am requesting.
Yeah, starting point, as I mentioned, that we have to figure out that how we can break the problems first. Okay, and after that, are we getting the optimal solution after solving the sub problems, and get using the sub problem solution to achieve the final solution. Are we getting the optimal solution? These things.
Okay, what you are
Okay,
telling
so
now, you are not yet ready, is it?
sorry.
You are telling now we are not yet ready for that type of practice.
Yeah, because of that, I'm saying that we have to learn some problem first. So, as discussed, 5, 6 problems are discussed in the week. After that, you have to practice on the assignments, like assignment we have given.
Mm-hmm.
So, still after that, you will get some idea how we can approach the problem.
Okay, we go
Okay.
with you. Okay.
Yeah. So this is not a formula-based thing. So this is based on the practice. Okay, so we are just giving some idea after solving some problems. After that, you can just think about the approach. So in the next problem, so same things in the previous problem. If you see this, so here we are doing this approach. We know this is a very easy problem, so we know this approach already. But so we also need to confirm that after solving the sub problems and using the sub problem solution to the achieving the final solution, and are we getting the correct solution or not finally. Okay, are we getting the optimal solution or not? So that things is also required to confirm. So are we getting the correct solution? So that things you have to figure out by looking the problems. Just take some simple problem, just a small problem, and just confirm that are you getting the optimal solution using this approach or not. Okay. And sometimes like we have discussed some coin problem in the previous week, in week 7 I think, greedy approach where some coins are given. Okay, so I'll just discuss again. So like 1, 2 and 5 and 6 and 10. Okay, or we can see that 8. Yeah, 8. Suppose we have infinite number of coins for each value. Okay, so 1, 2, 5, 6, 8, these are the value of coin, and we have infinite number of supply of these coins, and we want to just make some amount using these coins. So suppose that some value is given like 15. Okay, so how we can just achieve this value of amount by minimum number of coins? Okay, so first things is comes in our mind like this. We can use the greedy approach here. So we can start with the high value coin first. Okay, and we will select, we will check that. So this we want to achieve this 15 value. So we will select first highest value of the coin. So 8, we can select only one coins for this value because the value we cannot take 2, because if we takes the 2 then value will become 16. So we can select only one coin of the 8, that value will become 8. Now remaining value is 7. 15 minus 8, 7. And how we can achieve the 7? So we can select the next highest value. So this is the 6. So we our amount is greater than this coin value, so we can select one coin of the 6. So now this will be this is now 6. Now 8 and 6 is 14. Still 1 is remaining. Okay, so we can just we cannot take 5, we cannot take 2, we can take now 1. So one coin we can take of this value. Now we are getting 15 total. So total 3 coins we have required for this 15. So here this is the correct solution. We are looking this approach is correct. You can take some other example, but by chance for some value this greedy approach is actually failed. So for example, if we take this 11, okay, if we take this 11 amount, so you can see that we will if we are following this approach, we after selecting the highest value coin, then we will check what are the remaining amount, then we will select the next highest in this manner. So this is the greedy approach actually. So here if we select the same approach, so we are getting 8 equal to 8. Now the 3 is remaining. Okay, and then we cannot select 6 because the amount is less. We cannot select 5. Now we can select 2. So 1 into 2, not 2. Okay, and still 1 is remaining, so we will select 1. 1 into 1, now 1. Total amount is 11. So here we need 3, but we can achieve this 11 by 2 coins using this 5 and 6. Okay, so one coin of 5 and one coin of 6. Total value is 11. So this type of problem where you cannot achieve the solution by some greedy approach, and where you can get the solution by any permutation of the combination of the coins like this. Okay, so if we are solving some problems, and if you can get the solution by any combination of the values in between, so there is no way to get the solution by just sorting or by selecting some maximum or minimum things. So this dynamic programming problem is also discussed, used most of the time. It is used to find out the optimal solution, like this maximum, what is the maximum value, what is the minimum value, like this. So if the solution, to finding out the solution, you have to just look all the permutations for the possible permutation of the combinations. Okay, so in that case, you can think about the dynamic programming approach. So here you, to figure out so this greedy algorithm is not working. So what are the naive approach to solve this problem? Okay, so here we have just figured out this direct solution. So that means we cannot solve this problem using greedy approach by sorting the process and by selecting the maximum one like this. So what are the other naive approach to solve this? So other naive approach is to just find out the all possible combinations to solve this. So like you can select 1 and 2. Okay, if you're not getting solution, you can select 1, 2, 5. This is also not possible solution. Select 2, 5, 6. So all possibility of the combination of coins you can just try, and then you can achieve the solution. So this is the naive approach. Okay, but the complexity will be very high to solve this problem in that manner. So this type of problem you can solve by this dynamic programming approach. So in this case, if you have these number of coin like 1, 2, 5, 6, and 8, so you can just take that if your amount is 8, so here your amount is 11. So just distribute this amount like this 1, 2, 3, and till 11, and just you can make some tables. So if your amount is 1, then how many coins are required by this combination? Okay, so if your amount is 1, so this is the sub problem. Now we are just considering that if your amount is 1 value, so what are the minimum coins is required? So in this case 1 is required. Okay, so same things. Now we will increase the problem into a bigger part. So like we will just check for the 2. Okay, and here we have already solved this problem for the 1 amount. If we have already solved this problem for the 1 amount, so if any time it is required, what are the minimum number of coin for 1, then we will directly read the answer from this part. Okay, same if you are finding out the what are the minimum number of coins required for 5, and suppose we have to check this like we have available coin for 5 is, so we have possibility like this, we can just achieve 2 plus 2, so like this 2 into 2 and 1 into 1. Okay, so this possibility. So in this manner we will just think about that how we can solve this. So this type of problems where the naive approach, if you are using the naive approach, so you have to check all possibility to solve the problems. At that time you can think about the dynamic programming approach. Okay, so now we will just discuss some problems, so you will get idea. So sometimes we need only one dimension table to store the results. Sometimes we need 2-dimensional table to store the results based on the what data is given in the problem. So grid path. So next problem is grid path, and this is another problem. So here the problem is we have some grid. Okay, and we are just considering this lines of the grid as a path. Okay, and we can move only one step right and one step up at in the one step. Okay, so we can move only right and up, both 2 directions. So this is the one direction possible, this is the another direction possible. We cannot move down and we cannot move left. Okay, so if this type of problem is given like, and we are asking that how many paths are possible, how many paths are possible to reach at some point. So we are starting from this 0, 0 point, and this is the final destination like this. Okay, so this is just a target. Otherwise we can take any target in this grid, and we can find out the solution for that. So how we can achieve this? So you can say that there are lots of paths are available, but what approach you can use here? So naive approach, you have to figure out all unique path in some manner, and then you will get the solution. So any idea to solve? Anyone think about what approach you can use to find out the all possible path here? So there is one possibility with think that naive approach we can use, so we can just find out the one path, and we can just, so here we have to check all possibility in some way, then we can figure out. So there are lots of possibility here, because we can change the path after one steps every time. So in this manner, how we can solve this using the dynamic programming approach? So we can start the same things. So for this line, okay, so if we just consider that this baseline, okay, to the row, so we are starting from this 0 0 point, so this is the 0 0 point, and if all the points, if you consider on the same row, so how many paths are possible if you are following these two move, up move and right move, and same for the above one, okay, these points. So how many paths are required to reach at this? So this 0 point, this is 1, this is 2, this is 3, this is 4, this is 5, okay. So how many paths are required to reach 0 to 1 in this row, or 0 to 2, 0 to 3, 0 to 4, 0 to 5? How many paths if you following this two possibility of the move, one step right and one step up in one time? Can anyone tell me? How many unique paths are required from 0 to this first row, this first path, this path? Okay, so this is the one great line only. So how many unique paths are possible? Just look the this grid and think about that. Can anyone answer me?
So traveling horizontally.
Yeah, we have only two possible way to move here. Is we can at a one time we can move one step onto the right, okay, or one step onto the up. So in that way, this is the step. But how many paths are required on this line?
So if the coordinate is 2 0, then 2, 3 0, then 3, 5 0, then 5, like that.
No, this is the coordinate. So let me check here. So 5 we are taking first. Okay, so this is the 0 1. This is 0 2. Okay, this is 0 3. This is 0 4. This is 0 5. This is 0 6. 0 7. 8. 0 9 and 0 10. Okay, here in this side coordinate are like this: G 1 0 and 1 2. Not 1 2. Sorry, 2 1 2 0 3 0 and 4 0 and 5 0. So these are the coordinate of this line: 1 0 2 0 3 0 4 0 5 0. Okay, so actually the first value is representing the column number C, and this is the row number, like this. So if you want to come at this point from this first location 0 0, so how many paths are possible? Paths means the sequence of steps. We are not counting the steps here, we are just assuming one path. So you can see that there is only one path possible. If you want to come at this 0 10 point, you can come only by this path, no? One line. You can just go in that way and you can reach here, this point. This is the one path possible. You cannot come at this point by the another path. Similarly, on this row, Okay, if you want to come at this last point, so you can use only this path. You have to come at the 1 0, then you have to come at 2 0, 3 0, then 4 0, then 5 0. So this is only single path. That means one path is required to reach at any point of this line, 3 2, this 1 0. Okay, same for the vertical and same for the horizontal. So one path is possible for the both direction. If the first row, this 0th row and 0th column. So we can make this value as a solution of subproblem. So we can use this data as a solution of subproblem. So what we can just assign the value. Okay. So we can assign the value. That means if we want to come at this 1 0 point, so that means how many paths are required from 0 0 to this point. So how many paths are required? 1. Okay. Similar for the second point 2 0, how many paths are required? 1. So only one path is possible. So this one path is possible. So for this point also one path is possible. Similar for this line, one path, only one path are possible for each point on this row. Okay, so this is simple steps. We can assign this value on the each point on the 0th row and 0th column, because only one path is possible. So this is the sub problem. We are just considering that if we have solution. After that, we can simply solve this problem by we can start from the horizontal manner. Okay, so we will start from the first row, then second row, then third grid line, then fourth grid line in this manner, or you can solve this using this vertical manner. Okay, so first grid line, second grid line in the column. Okay, in this manner. In any way you can solve this. So for this point, this is the point, we can see that this is this column, this is row. Okay, so this is the second column, sorry, 0 no? So this is 1 and this is the same 1.1. Okay, so this is the 1.1 point. So how many paths are required to reach at this point? Okay, from 0 0. So now here you can see that you can come at this point by this path first, and another path is possible from this side. Okay, only two paths are possible. So the solution for this is 2. And you can see that we are coming from this side and the lower side. So we can also use the value which is we have already solved. So how many paths are required for this point? 1. And how many paths are required at this point? 1. Okay, so we can also sum up this value. So 1 plus 1, and we can achieve the solution for this point 2. In this manner, if we solve this, so for the next point, so for this point, so how many paths are required to reach at this point? 1 1, and we are now solving now 2 1 point. Okay, so we know that there is one path possible from this side. Okay, but at this point we can come from two sides, two different paths. So that means two paths are possible from this side and one path is possible from this side. So two value we can read from the previous subproblem solution. So this is the solution of subproblem. Okay, so this 1.1, we will store the solution of this point, and next time we will directly read the solution. So how many paths are required at this 1, 1, 2. Okay, and how many paths are required? The lower part 1. So 2 plus 1, 3. That means at this 2, 1, we need total 3 paths. We can come at this position by 3 paths. And we are using the solution of subproblem here. Okay, same things we will repeat for the complete process. Now we have 3 paths at this point. Okay, so that means 3 paths we can come here on this side, and from lower side we can come only from the one path. So that means 3 plus 1, total 4 paths is possible at this point. Next point, same, 4 plus 1, 5. Okay, now 5 plus 1, 6. That means this at this point, this is the 5 comma column and row. Okay, fine. So this is the point 5, 1, 6 paths are possible. So now we are just solving the we are using the solution of sub problem. We will repeat this process. So next level you can see that one path from this side and lower 2. Okay, so 1 plus 2 3 here, and now 3 for here and 3 for here. Okay, so 3 plus 3 6. Sorry, this is 6. Total 6 path. 6 plus 4 total 10, and 10 plus 5 15, and 15 plus 6 21. So we are just getting the solution, and this solution is correct. So we will repeat this process and we will get the solution for this position if we will repeat these things. So this is the one dynamic programming approach we can solve using this. So the first step is, so we can just assign the base case like a sub problem solution. So we are assigning the value of the base case. You can see here P001 base case, and Pi equal to 0 equal to Pi minus 1 0. So this is the bottom. So let me check this recurrence for the relation. So this is the first condition is given. So at every point, so we can either come from up from I equal to j minus 1. So that means j minus 1 is representing the lower part, lower side, and we can come from on left side. So this one. Okay. So every point we can get the solution by this solution. What is the previous this location solution and what is the this location solution? Okay. So this is the things. Each path to these neighbors extend to unique path to I comma j. So this is the things. And base case we will assign like this. So you can see the solution here. So initially we have assigned all 1 on the first and 1 on the 0th row and 0th column. After that we can achieve the solution. And the next version of the problem is given like if any blockage is given on some point. So suppose any blockage is given. So here all are open path. Suppose if any blockage is given, so we cannot use this point as a path. These are some like blockage like, okay. We cannot use this path. We cannot come from this point. So at this position, how many paths are possible? So in this case, so we can use the same approach, but we will assign 0 solution for you because we cannot use this blockage. So we will directly assign the 0 path on this point. So next point, we will just use this 0. Sorry, Ravi?
Why there is blockage, sir? Why we are not using that?
No, this is the problem actually. This is one possible problem. If it is mentioned that you cannot use this point for the path. You cannot cross that from this point. Okay. This is one type of problems. It is also possible to ask if some blockage is given on the road, you cannot use that road to cross. Okay. So how many paths are possible then? So what we will do, we will simply assign the 0. So we are solving this problem from bottom up or left to right this manner. So you can see we are using the same approach, 1 plus 1 2 and 2 plus 1 3. So we will perform the same approach, but at this point we will directly initialize 0 because we cannot use this path. That means there's no path possible at this point. So we will use 0. So next level you can see 6 plus 0, we are getting 6 path. So to reach at this point, only 6 paths are possible because we cannot come here, okay, and we cannot come this direction because this is the blockage. So we can only use the approach from this side, like in this manner, okay, like this, or there are multiple things. So at this point, how many paths are possible? So we have already calculated. Now 6. This side we cannot come, so we can come only from this side. So on 6 plus 0, total 6 paths are there. Same things, you can see that 26 plus 0, 26 we are getting. Now we can continue the process and we will get the total number of steps. So this is 1 3 5 8. Previous it was some more. Okay, if you solve this problem, then you will get the high number. The one other most the problem is in the same things. So now if blockage is given in this manner, so same problem we are discussing 0 0. Now blockage are given on these points. Okay, so in this way we can directly assign 0 value on all, because there are no path are possible, and this is simply 1 1 1 1 1, and this is 1 1. Like this. Okay, so in this case actually what happened, this all calculation is become wastage. So we are solving this problem, so all this calculation are not useful, this yellow part, because finally in this steps we have to add only 1 plus 0, so 1. Okay, so 1 plus 0 1, 1 plus 0 1, and 1 plus 0 1, and similar from this side, so 0 plus 1 1, so this will also only one path possible, and 1 plus 1 2, only two paths are possible. So if we are following this approach and problem is given like this, so all these calculation become wastage. So sometimes the dynamic programming is still better in general, memoization techniques or dynamic programming. Okay, oh, just inside the water. So this example is given because this time we are filling, we are using dynamic programming approach, and dynamic programming for dynamic programming approach we will take two-dimensional matrix for this to fill the data. Okay, and later we don't know that what is the future position. So still, if you think that this all operation which we are calculating in this part, yellow part, this is not useful to solve for the final solution, but still some part is wastage here, but still this is better than the normal approach, naive approach. Okay, so which we generally use the iterative solution or recursive solution. This dynamic programming is still better than the normal iterative solutions, if you find out the another solution for this. So this is the one problem which we can solve using this dynamic programming. So
Sir, what does the yellow region represent?
this is the actually wastage calculation in the dynamic process, because these graded part actually actually here these are the blockage. This black part is actually are the blockage. Finally, we cannot use this path, and we are solving the problem in the bottom up approach. Okay, this manner. So we are starting from 0 0 point, and we are blindly solving all the positions according to the dynamic programming approach. But later we found that this is the blockage point. So now all this yellow region part is actually wastage. No, this part information is required to solve this problem.
So only you can go through the periphery, no? You cannot get inside and.
Yeah, because we will follow the process, what process we have developed for the dynamic programming. We will still follow this. We will solve all the points. Okay, we will solve all the points, but these points are actually wastage in our to get our final solution, because after reaching at this point, this is not used. Okay, so after that this is by default filled by 0. So we are not using these value to get the final solution.
Sir, so for such a blockage pattern, memoization would be better. Is that what it's saying?
Yeah, it depends on the how we are solving the problems. Okay, so if we are solving the problems, yeah, correct, bottom up approach. Yeah, you are correct. So memoization things, we always start from the bottom up. Okay, in the recursive manner from the top side, and we just look. So we can directly, this is the blockage part, we can directly assign with 0, and we can start the problem from the top side. Okay, and from this side, if we found that, so we will fill this first, and we will fill this first, and then if we look the solution of this, so we can directly achieve the solution. So what is the solution for this? So this is 0, and we can figure out the solution from directly here. Okay, so this is 1 and this is 0, so 1 here. So from top side, we will just get the solution, and from same for the this side, and no need to move this side. So in this
Sir,
case, the memoization is better. Uh, Dynamic programming, we solve the problem from the sub problem, okay, lower part. And in this case, the dynamic programming is taking more operations, but that are actually not used later. So this is wasteful.
as given now, there is only two ways you have, no?
Yeah, two paths are possible. But
Only
how
two
we
paths.
will, yeah, how we will approach to solve this problem? So if we use the memoization, so memoization is basically top down approach. We start from the main problem. So this is the main problem. We will start from this side. Okay. And here we are calling two types. Okay, so what is the solution for this point and what is the solution for this point? If solution is not available, then we will call again this side. Okay, so this solution is available, so no need to move from this side, because you will directly read the solution from 0 here. But here you will repeat again this calling from this, because this is initially not filled. This column is not filled, so this will be filled from this side. Okay, so here when we will reach at this position like this, so this is the calling structure of top down approach. Okay, and when you reach at this last position, so you have already solution for this one and then 1 0, so you will get this one. Okay, then 0 1, so you will get this one like this, and you will fill this in manner reverse back. Same for the this side. First you will call in this manner and you will get the solution from here. So you will never enter in this yellow region.
What way it is superior than a bottom-up approach?
Sorry.
What way it is better than a? You said that top-down is the better method, no?
Yeah, in this case, that top down approach is better.
Why bottom-up is not good? Same level of complexity only is there, no?
No. So in bottom up approach, we are solving the sub problem first. Okay, so you will solve all these points value. What is the value for this? What is the value for this one? In this
No,
manner,
no,
you
no,
will.
no. No, I will not get into the orange region, no, on that shaded region.
No, how you know that? How you know that this is the orange region? You don't know, no? You will only follow the process. So according to the dynamic programming approach, you will enter this region. So this yellow region is given in this diagram, but you don't know where is the blockage.
Oh, you got to continue your effort until you see
Yes.
the block.
Yeah. So once you reset this blockage, you will fill this 0 value.
Oh, that's a waste effort.
So this is the total waste operations. But if you follow the memoization techniques, that is what this top-down approach. In this manner, when you will reach this blockage, you will get 0 directly written, and you will not call this part again from this side. Okay, that recursive call will not be generated, because this is from this position you will directly get the solution 0.
Okay. All right. Thank you.
Okay, so here actually memoization is better, but this is some case we are getting this type of situation. But here we have to use the recursive approach, so that recursive cost is actually increased. So in general case, when this type of some rare case is not there, then most of the time dynamic approach is better. So now next problem is longest common subword problem, which is discussed. So longest common subword. So this means what is the problem is actually first understand that you are given two strings, okay, and you have to figure out the longest common subword. Subword means continuous substrings which are common in two strings. So here example is given like this: S E C R E T. Okay, these are two. First string is given, second string is given B I S E C T, bisect. Okay, secret and bisect. So what are the longest common substring is there? We can also think of the longest common subword or substring are both are the same things. Okay, so then we have to figure out that what are the longest part which are common in these two strings. So if to think about this problem, so you have to by the naive approach here also. Okay, by the naive approach, you have to figure out all possible combination which are actually matched. Okay, so same things. There's no way to solve this problem in by some greedy or like the sorting or these things, because here we cannot change the sequence of word, because these are the some word or strings, so we cannot change the things in this given strings. We have to figure out this. So some, so from we can say that some part of the initial of the first strings may be matched in the later of the second strings. Okay, so we cannot follow any the like loop things. So this sec, you can see that this part, this is the initial part of the first string, but it is matched here sec. Okay, so how we can figure out this when the some part of the one string will match into the another part of the substrings. Okay, so there is no way to easy way to solve this problem. So how we can use the dynamic programming in this, and we can figure out the same dynamic programming approach. That means we will start from the sub problems and then we will get the final solution. So what we can think about, so we have given two strings, so we will maintain two-dimensional matrix for this. Okay, so to fill the solution. So this, you can see that for secret and this bisect, we have two strings. So we will just create a total number of columns based on the first strings, and we will just assume one additional. Okay, so this is the first string, and one additional column we are taking to make the base case. Okay, and this is the second strings. We will make the rows, number of rows according to the what are the second string, and we will add one more rows for the to making the base case. So what is the meaning of base cases? What are the common? So here you can see that this dot, this is means empty things. Okay, so there is no string here. Suppose you are given, so suppose this is the s1 string, this is the s2. Okay, s2. If s1 is given like this a b c, okay, and s2 is not given, empty string, so what is the maximum common solution for this? 0. Okay, what are the common substring which is matched here? 0. Okay, if second string is empty, so because of that we are taking this additional dot, and this is representing the empty condition. Similar for here, if s1 is empty and s2 is given like a. Okay, now there is no string for s1, and if s2 string is there, so that means still there is no common things, then we can assign the 0 length. Okay, so because of that we are taking this one additional dot which is representing the empty strings. So what we are doing, so by taking these two condition, and we are just assigning the solution for the base condition. So, and you can see that we will start solution to solve this problem from this side. And what we are taking, if this both strings are empty, okay, so if this is both this dot is representing and this dot is representing, so what is the value for this here? If okay, so we are just assuming, we are starting from the base condition. So s1 s2 both are empty, so what are the common length is 0. So this is the first value we can initialize directly because we know the solution for this. Okay, if suppose we are taking this first, so this is the s2, okay, and this s1, yeah, s2 we are taking empty dot. Now we are just adding one character for s1. Suppose s1 have this string t, so still now you have t and s2 is empty, still you will get 0 common length. So here we are calculating the maximum common length of the substrings. So 0 is the solution for this case. Same for if we also add one more character. So now you can see that we are just starting from the sub problem, little problem. So et, now we are just assuming that s1 is et but s2 is empty, still solution is 0. So if any string is empty and any other string string is actually contains some characters, so always answer will be 0. So we filled this row by 0 by default. Okay, same for the this side. If this first string is empty and second string contains some characters or some things, okay, answer will be 0. So we will directly filling this solution. So now this is the solution for the base case. We can directly fill this solution by according to our knowledge. So this is the only one possibilities of the solution. After that, we will use this solution to solve the remaining problem. So now we will just make the inductive formula for according to this. What we will do, now we are assuming that we have S2. So we are S1 and S2, okay? And we are taking this last character we are taking, okay? So T. Suppose S1 contain T and S2 contain this T, okay? So what will be the value for this position? Okay, so you can see that if both characters are matched, T and T, this is matched, so that means the length of this character is 1. So we are filling this 1. Okay, and now we will check this. And we are also adding the previous solution. So how we will just understand that how we can use this previous solution. And in this problem, we are figuring out the continuous common string which are matched. Okay, so when the one string was empty, then solution was 0. So we will, if the characters are matched, we will always read the diagonal value and will add the one value onto the diagonal value, because this diagonal things is representing the continuous sequence. Okay, so you will get these things after some value. Okay, so and we can also create the inductive structure according to that if the characters are matched. Okay, if AI does not equal to BJ, if characters are not matched, we will directly fill 0. If both value are matched, we will read the diagonal value and will add the 1, because we are interested to find out the continuous sequence which are matched. So because of that, we are adding the diagonal value. If previous, well, you can see that here there is no matched, then we are adding 1. So now this part at this position where this second string only contain T and this first string also contain only T, what is the maximum common length which are matched is 1. Okay, now next part, if you see this, if S2 is only T, okay, S2 is only T, S1 we are adding characters. Okay, so if we are adding ET, so at still this position, you can see that this position. Okay, so this position is representing for this case. So E and T is actually not matched. Okay, so E and T, this, yeah. So this is E and T is not matched. So the what is the continuous maximum length is here 0. So we will fill this by 0. Similar for this R and T is not matched. We will fill 0. Then C and T, this is not matched, 0. Okay, so 0 0. This row we will fill by 0 in this manner. Okay. Now we will increase the size of this S2. Now we will fill this way. Okay, so now S2 will become CT. Okay, and same things we will repeat for the S1. So we are first considering that if S2 is only contain T. Okay, so T and C is here. So we are looking only this rows. We are looking only this rows and this column. So C and T are not matched, 0. Okay, and C and E, these characters are not matched, 0. So 0 not matched. Okay, here you can see that C and C, this is matched. Then we will read the diagonal position, because this diagonal things is representing the continuous matching. Okay, so what are the previous solution which are already matched before this C? Okay, so what are the previous solution? What are the strings which are coming after this C, and how many matching we have got this position? Okay, so previous this T and this R is actually not matched, because of that this is 0. But now this C and this C is matched. Okay, so we have just initialized by 1. So 0 plus 1, 1. So same way, C and E is not matched, 0 we will repeat this process. Once again, E, we will just look about this, see here. So 0, E and E is matched here. So we will just add 1 from this side. So what is the 0? 1. So E and R is not matched, 0, 0. Now you can see that this E is matched with this E again. Okay. So after this E, what are the continuous sequence which is already meshed? Okay, so you can see that C, here we have one value, and we will add 1 plus 1, 2 here. Okay, so this is representing that two continuous characters are meshed. Okay, so 1 plus 2, we are getting this 2 here. Okay, and next level we will fill this matrix in this manner, and here you can see that S and S will matched in this position. S and S character are matched, and we will check what are the previous diagonal solution is 2. So 2 plus 1, 3. So this is representing till this S. What are the continuous sequence which are matched? 3. Okay, both list, and we will repeat this process. And finally, we will just revert the answer. What are the maximum value in our this matrix? Okay, so there are multiple. So here you can see that we are getting 1, we 2, 1, and maybe some way like 1 and 2 you will get some place. Okay, so there are multiple possibility of the matching in two string. Okay, so this part is matched. Maybe another part is also matched in the same strings. So you will get the all possibility of the matching maximum length, and we will return the what is the maximum value in this matrix that is actually representing the maximum length common subword or substring. Okay, so this 3 is actually, you can see in the whole matrix we are getting this is the maximum value 3, and this 3 is representing the maximum length of the common subword in two strings which is given. So we can write the solution for this problem, and we can use this inductive structure. Okay, so how we can solve this using the dynamic programming approach? We will just follow this. So now you can see the code for this, and this is the dynamic programming code, solution code. So first, what we are doing, we are just creating a zeros matrix. Okay, and what is the size of this zeros matrix is? What are the size of first string and second string? Based on that, S1 size is M, S2 size is N, and we are creating one more, M plus 1 and N plus 1. Okay, and initially we are assigning the 0 value for all place. So we are assigning 0 value, so that means this by default this base case is also filled. Okay, so this is also filled, so no need to fill this separately. So all value are filled initially 0, and you can see from the last by this max W, this is representing the result. Okay, what max value we are getting in the matrix. So we are just running 2 loops, and you can see that we are starting from the bottom and bottom right. Okay, so n minus 1, same m minus 1, that means bottom of manner, and we are just using this inductive structure if the both characters are matched, S1R and S2C. Okay, if both characters are matched strings, so we are reading the diagonal value and adding the 1. Okay, and filling the matrix. If characters are not matched, we are filling 0. And finally, we are getting we are comparing the previous, what is the max value, what is the previous max value. If we are getting the more value compared to the previous max value, we are updating this. And finally, we are returning max W. So in this case, what complexity is there? You can see that. So we are just using this 2 loop where the size of first loop is n, another loop is m. So total complexity is only n into m. You go n into m. So in this number of operation, you will get the solution for this problem. Okay, this LCW. Any query in this?
Sir, can you scroll down? Is there a for loop you have applied here for C in range n minus 1 to minus 1 to minus 1? Why you are starting from this -1 here? Can you explain this?
This n-1, because we are taking this, if we are following some approach, we are starting the solution from this side. You can also change this. What you can do, you can assume your string from this location, okay, and from this location, from this point, and first point you can assume that the empty point, and fill this first point by 0, and after that fill and get the solution in this matrix. So you can change your solution accordingly, where from you are just looking, where from you are filling the base case and how you are getting the solution. Okay, here we are solving this problem from the this top corner. You can fill this matrix either column wise, okay, or you can fill either row wise, or you can also fill diagonal.
Okay.
All three manners you will get the solution, because every time we need the value of diagonal things. Okay, we are looking only the diagonal value. If the characters are matched, we are looking for the diagonal value. So base case should be there. If when we are starting the process, then base case should be there. Suppose here you can see that at the time of first filling, T and T both are matched. So we will check what is the previous solution. What is the previous solution we have in the diagonal. So if this value is not filled, you will get the error in your code. So because we have filled this last row and last column as a base case, so we have to start from this side. Okay, you cannot start from this position because you don't have the previous value if this value, these characters are matched.
Okay.
Okay, so where is base case? According to that, we have to start. So because of that, we have to start from n-1 and m-1. So this is the first column. Okay, and we have taken one more row and column, so which we have already filled zeros. So we are using that solution from this diagonal plus 1. Okay, so in this manner, you are getting the maximum length. But if suppose if this question is asked, what is the common substring? So that type of problems you cannot sure that you will get you will revert all answer, all possible answer. You will get you will return one possible answer, but this is not always true. You will return the all possible answer. Or what you can do, you can return that also. So suppose we are asking that what are the common substring which have the maximum length. So there are multiple possibilities. Suppose we are taking this SECRET. Okay, and another string is like this RET and SEC. Just reverse two part. Okay, so this sec is matched with this sec. Okay, and this RET matched with this RET. Okay, in this manner. So in this case, both length is 3. So if answer is question is that what is the maximum common length of the maximum length of the common substring? Okay, then answer will be 3. Okay, so both the string have the 3. But if we ask that what are the strings actually which are common, so there are multiple possibility of the answer for this. So you can see that in this example there are 2 strings which have the maximum common length. Okay, maximum length. So how you can return the answer? So from this matrix, okay, from this matrix, where you are getting the maximum value, you have to figure out that where you are getting maximum value. Okay, suppose you are getting here also, so 3 2 1 like this. Okay, so here you are also getting 3, here you are also getting 3. So you can figure out that where you are getting the maximum value, and after getting this position, just move diagonally to the down. Okay, and just at the time of reading the strings, just check at what is the common string which at this place. So what is the row and what is the, or you can read any one side, one string. Okay, so what is the row value, row character at this 3 values? So this is S. Okay, what is the character at this? Just move this in this direction, 3 2 1, and read the character. Okay, so SEC, you will get this SEC. Okay, when you reach at this 1, you can stop. So this is the last character which is matched. So you can read the strings in this manner. Same things you can repeat for the another place where you are getting the same 3 value. Suppose you are getting 3 at this place also. So you will just move diagonally and read the character, what character are coming. So in this manner, you can also return all possible strings which are matched and have the maximum length. Okay, so this is also one possible problem which can be asked if suppose two strings are given and asking that what are the possible common substring which have the maximum length. So you can just get the solution in this manner. Okay, so this is one problem which we are solving using the dynamic programming approach. So related problem is also to this is longest common subsequence. So what is the difference between this longest common subsequence and previous problem? So here is also given two strings. Okay, same example is given. So let me check this. So S E C R E T and BISECT. So longest common subsequence means you will follow the order, but you can skip the characters. Okay, but you cannot change the order of characters. Then you will figure out what is the length of a common subsequence. Okay, so here you can see that this S and S is matched. Okay, same. Next is E and E is matched, and C and C is matched. But here R and E is coming, which is not matched with the next character, but later T and T is also matched. So for subsequence, okay, so subsequence means you can skip the character in between, but you cannot change the order. So here, if you're getting the order of characters, so S E C T, and same order you are getting from here, S E C T. Okay, without changing them. So what is the maximum length of the common subsequence in this manner? Previous problem, we are only interested to find out the continuous sequence without skipping any character. But here we can skip the characters. So in this problem, so we will just use the similar type of approach, but here actually we can skip the characters. So we will change the logic accordingly. So previous time you have seen that when our characters are matched, so AI equal to BJ. So we are using the same things. Okay, we are just reading the diagonal value I plus 1, J plus 1 and adding the 1. But this time, so if characters are not matched, then we are not assigning the 0 value. Okay, we are assigning the maximum of the left or the bottom of this position. Suppose we are filling at this position. If characters are not matched, then we will check what is the lower value and what is the right value and what is the maximum among both, and then we will fill at this position. Because here we are filling in this direction, so we can skip the character. Because of that, we will maintain the previous matching on the same order. What previous matching we have already find out, then we will keep maintain in our matrix. So if you can see that we are following the same approach. We are filling this row by 0, this row column by 0 first, and then we will start filling by this, like, okay, so we can fill by the row wise and column wise in any order. So if we are supposing filling the column wise, so we will fill this location first, and here T and T is matched. Okay, so we will simply add the diagonal, so 0 and 1, 0 plus 1, 1. But if you can see C and T is not matched, now we will just choose the maximum, because here we are finding out the subsequence. So we can skip the character. If we have two strings, so T and CT, so what are the common subsequence we have? We have still 1. Okay, we have still 1. So because of that, we are maintaining the previous solution. We are not discarding the previous solution. Okay, so 1 we are selecting. What are the maximum solution for this? If we have only this strings, so 1 we are choosing here. Okay, the max of these two. Similar for this side, E and T. Okay, so here still now if we are adding E in this, so what is the solution? So we are selecting the maximum among all these two. So 1. Okay, same for 1, 1. We are repeating this process because every time we have only T, but in the another string you can see that we have T, C, E, S, I, B. So solution for each stage is 1 because we have this part is matched. Now if we add the next position for this, okay, so you can see that we are adding now, so this is failed, yeah, this is T and this is E, so this character is not matched. So we will look what is the maximum solution we have. So 1 and 0, so 1, okay, so we will just using this. So this process we will repeat, so you are getting the same things, 1 for the every row. And when we including this C in this, okay, so and here T, so C and T is not matched, so 1, and this position is still C and E is not matched, okay, then is not matched 1. Here you can see that C and C is matched, okay, so C and C matched, so we will check what is the diagonal solution is there, 1, because we have already find out if this string is T and what is the solution of the remaining string. So T we have the 1 length, and if we include C, so now S2 will become CT, and till now we have CRET. So you can see that we have the maximum length 2 which are matched, so this C and T. So because of that we are storing the previous solution, maintaining, okay, so 1 plus 1 2, we are getting 2 length here, okay. So in this manner we will fill this matrix. If our characters are not matched, then we will pick the maximum among left or right or bottom. If our characters are matched, then we will add 1 on the diagonal value. So in this way you will get the you can see that E and E is matched now here, so we are adding diagonal value 3 here, and now S is matched 4, and after that I and S is not matched, then we will just keep this maximum of right and bottom, so 4 and 3 4, and 3 and 4 4 here, okay. And in this case we will return what value we are getting in this tops, okay, so that will represent the solution for this problem, longest common subsequence. So what value we are getting at this position, that will represent the longest common subsequence length, okay. If you want to find out the longest common subsequence, same things, multiple solution are there possible, but we can return one possible answer by this. So you can just start from this corner position and check that what are the value of this right side and bottom side. If any value is similar, okay, suppose this 4 and this 4, so that means you can move onto the similar side. If suppose if this is also 4, then you can, that means there are multiple possibility of the answer, so you can move either this side or this side, okay. If value are not same, no, if value are same you will move diagonally, if value are not same you will move to the maximum side, because we are coming in this way. So if value are not same, just move the maximum side, okay, and same repeat the process again. So 4 3 and 4, so same maximum is below, so maximum. If value are same 3 and 3, you can see, okay, then move diagonally, and when you are moving diagonally just read the character, okay. If the both right and bottom value are smaller and same, so at that case just move diagonally and read the character. So this first character will be read, and you have reached at this position. Now check what are the right value and bottom value. If both are smaller and equal, just once again move to the right side, and character are E, okay. Same things from the 2, C and C is matched, C will also come, then 2 to 1, then this T will come, okay. Now you will move in this maximum side here, and when you are reaching at this position, yeah, so at the, so from this position when you are reaching from to 0, then this T will come actually, okay. So at this time C is come, now we are not moving there, yeah. So you can just figure out that one possible solution, common subsequence, which is actually we found that. Otherwise most of the time this this type of problem is asked for the value, what is the length of the maximum common subsequence. So you can return the solution for by this matrix, what value you are getting on the first location. So now you can see the solution. So same things we are following here. So we are filling by 0 matrix, then we are starting from the lower side. Now just change the inductive structure. If characters are same, then we are adding the diagonal value by 1, otherwise we are just reading the bottom and right value and returning the maximum to this place. And after that, we are returning this LCS 0, 0 locations value. That will be the answer. Okay. So this is one approach which we are using here, dynamic programming. We are starting from the sub problems and then getting the final answer. And next is added distance. What is this added distance? Same thing, two strings are given. So what modification is required in one string to convert that string into another strings? So like similar S, E, C, R, E, T, and here by S, E, C, T. Suppose we want to, this is S1, this is S2, okay, and we want to convert this S1 to S2. So what are the minimum number of operation is required to convert one string to another string format? And you can perform some operations like you can remove, add, and update. Three operations you can perform. So you can remove the character, you can add new character, you can update the character, change the character. So by using these three operations, how many minimum number of operations is required to convert one string to another string? Okay, so in this string you can just look this SECRET, and we want to convert this as this string into a S2 string. So how many minimum number of operations required? So logically, if you just follow this any random approach, you have to figure out all possible of case, but we can use the dynamic programming here also. So if you look this, so like this, we are taking some simple example like Monday. I think this is given in one question, and Tuesday. Okay, and we want to convert this Monday to Tuesday. So how many number of operations are required? So you can see that this DAY, this part is already meshed, but in this part MON, so here TUES, all are actually different. So what you can do, you can just remove, because the this side we have 4 character, this side we have 3 character. Okay, so there is no common in this, so we cannot reduce the operation, but all characters are different. So what we can do, we can remove one character from this side, and we can update this N to S and O to E and M to U. So here 3 update operation we required, and 1 remove operation we require. So total 4 operation we require to convert Monday to Tuesday. And same things from this side. If we want to make this Tuesday to Monday, still you have to remove 1 character from this first string, and you have to update 3 character to MON. So 4 operation is required. So this is the minimum number of operations is required. So how we can figure out this added distance? So this is called as a added distance, and this is very useful algorithm to find out the copy things. Okay, so if you know the plagiarism, and I think many of you are maybe you are doing the AppDev project. Okay, so that how many so if you copy the code or copy some document from the other documents, so how this plagiarism software actually identify that how much part is actually copied from other document? So they actually use this type of algorithm, either LCS or added distance. Okay, LCS is also representing the same thing, common things. Okay, same things, added distance. So what are the minimum steps are required to convert one document to the another document? So that if the value are less, okay, that means your document are high, there is a high similarity in your document. Okay, if this added distance is very less, that means both documents are similar. If this added distance value is high, that documents are not similar. Okay, so this added distance and this LCS, this type of algorithm is actually used in this application, in the plagiarism application, finding out the similarity in document like this. Okay, so this algorithm is also very important in the real life applications and are commonly using in this plagiarism software. So in this application, in this algorithm, we are using some different inductive structure. So here what we are doing, this AI equal to PI. If characters are same, so we are not performing any operation here. Okay, so because of that, we are directly reading the previous value. Because here we are finding out the minimum things, minimum number of operations. So here our goal is different. We are figuring out the minimum number of operations. If characters are matched, so we are just reading the previous matched value and we are not adding anything. No operation is required. But if characters are not matched, then we will figure out that what is the minimum value on all these three places: diagonal, right side, and bottom. Okay, what is the minimum solution for the previous sub solution? And then we will add one, because here character is not matched. We have to make similar. So we will check the all possible of minimum solution till that place, where from we are getting the minimum number of edit distance. So we are figuring out this minimum value of all these three locations, and then we will add one, because one operation we required, either update or edit or delete. So we will use this inductive structure in this problem. And now you can see, so you can see that here base case is different. If both strings are empty, then there is zero edit distance. That means there is no changes required, so zero edit distance. But if any string is empty and any string is contains some characters, so some operations are required. Suppose one string s1 is t and s2 is actually empty, and you want to make both are same, so you have to add some operation. So here there is one character, there is no character, so here you have to add one character, so t1 operation is required. Okay, if one string have et and second string have empty, okay, empty, so that means you have to add at least two character to make similar, so 2 is required. Okay, in this manner we will fill this 1 2 3 4 5 6 if one string is empty. Okay, similar for this side, 1 2 3 4 5 6 if one string is empty. After that we will just figure out that if characters are same, then we will read only diagonal value. So you can see that t and t is here, so that means 0 to 0. We are not adding any operations because, okay, so we are no need to change, then 0. If characters are not matched, then we will figure out that what are the minimum value among all these three neighbors, right, diagonal, and bottom. Okay, so for this location side, like C and this T, okay, this position. So what are the minimum value among all these three side? So here we are getting 0. So 0 plus 1 will become 1 here. Okay, from this side, because we are getting the minimum steps, minimum operation, edit distance, so we will add 1 here from the minimum. Okay, because here our goal is to find out the minimum number of steps to change. So we will follow this, and you can see that later what value we are getting at this position, that will represent the total minimum number of operations required to change one string to another strings.
So for 0, this thing is not applicable. Like in the line 5, 0.
Where this one?
Yes, sir.
So what this value is representing actually, if you have t string in one, okay, so s1 is t, okay, s2 is also t, only t. So what operation you require to change? 0, na? So initial it was both are empty, so this location is representing if both strings are empty, that means no operation is required to make similar. Same here for this location, if characters are, we have only one character here and one character here, like this, so still no operation is required to make similar. So because of that, we are reading the diagonal value. So 0 plus 0, 0. So we are just reading the diagonal value and storing at this place. Okay, but that means if characters are same, no operation is required. So we will not increase or decrease anything. But if characters are not matched, so in this case we will choose. So for this position, so like why we are taking this as a 1. Okay, so in this case we have one string, this s1 we have et. Okay, et, and this s2 we have only t. So when we have only this string, so this was we have already solved previous. Okay, so this t and t we need 0 operation. Okay, and when we have et and 0, sorry, empty string, so this is the case of this one. Okay, not this one, we are looking this. Okay, yeah, this 2 operation is required. Okay, so this is representing we have one string empty and another string in 2, so 2 is required. Okay, and this diagonal, this case when we have t and empty, we have 1 operation required. So we will look what is the minimum value among all these 3. So this is 0, and we will add 1. So this is representing this case. So we have the previous solution, minimum solution for this condition when both t are matched, and we need to add only 1 operation. Either we can remove this or we can add this side et. So only 1 operation is required to make similar. So because of that, we are adding 1 value in the minimum of all these 3. Because our final goal is to find out the minimum number of operation. So because of that, we are selecting minimum value among all 3 and adding 1.
So we are checking this only when both the strings are different.
Yeah, both characters are different on this side. Okay, so each location, so if you are looking for this position, just check what s is there and this is e. Both are different. In this case, just figure out what is the minimum value all these 3 sides and will add 1. So here this is 1, 1 plus 1 2 in this manner. Okay, so in this way you will fill this matrix. So this is simply size n into m. It will take n into m operation, and finally you will get some value here at this first location, and that will represent your number of operation which is required, minimum number of operation. Okay, so if you see the code, so same things we are performing, we are filling by 0. Then you can see that here base case is different, so because of that we are filling this base case by these 2 loops. Okay, and finally we are performing the same thing. So we are just using 2 nested loop. If characters are same, then we are just reading the diagonal value and putting at the same. If characters are not same, else part, then we are reading the all 3 place value. Okay, diagonal, then right, and then bottom, and finding out the minimum and then adding 1. And that value we are putting at this, and last we are just returning this 0 0 location value, and that is returning the minimum added distance. That means we need at least 4 operation to make this bisect into secret or secret into bisect. At least this 4 operation is required. Okay, so bisect secret. Okay, 2 strings are there, so we can use this s, e, c and t. These 4 characters are same, so what we can do, s, e, c, t, these are matched, and here this is also matched. Okay, so s, e, c, t, and remaining part, how many operations are required? So from b, this remaining which are not matched. Okay, so this is the bi part, and this side, this r and t. Okay, so any character are not matched in this part. So what we have to do, we have to update this okay, also order is different. Okay, so we are just we want to convert one string to another. So if we are converting this to bisect to secret, so what we have to do, we have to add this b and I in the initial, but we have to remove these from the backend. Okay, so 2 operation for the adding and 2 operation for the removing. Okay, so we will remove this r and this E, okay, R and E. Then we will get the same. Adding one this B and I in the starting, but we have to remove these two characters from the beginning and in the middle part. Then you will get the same bisect. Okay. So now you have the same, both strings same. So 4 operation is at least required.
Sir,
Hmm?
can you please explain the line number 14, where you are taking the minimum of these three? Line number 14.
Yeah, this one.
Yeah.
Yeah. So this is the diagonal value. Okay. And this is the bottom value, and this is the right value. So all these are the matrix value we are reading from here. So if any characters are not matched, okay, if any character are not matched, so suppose we are looking for this position. If characters are not, so here characters are matched, I think. Okay, C and matched. So suppose just look only this side, this 3. Okay, so in this direction, if we are getting I and E, both characters are not matched. So we will check what are the previous solution we have with the minimum edit distance. When we have the string of this and this. So what solution we have which is minimum?
Why we are taking minimum, sir?
Because final goal is to find out the minimum distance, minimum edit distance, na? So because of that, we are selecting the minimum. In this problem, we are figuring out what are the minimum number of operations required to solve this.
So how we are confirmed that taking the minimum of all the three things gives the minimum in the position?
So if we are solving some sub problem and every time we are getting some solution, if we are picking the best solution from the sub problem and then we are adding one, so that will definitely generate the optimal solution, minimum solution. If you picking the maximum value, definitely you will get the maximum value in the later. Here our final goal. So here what you are doing, suppose if you have the main problem like this P, and this problem is coming, you are getting the solution from 3 sub problems. So like P1, P2 and P3. Okay, and you can just pick any of these problems to solve the final problem. And here you have the solution for like this 1, 2 and 3. Here 2 steps are required, one steps are required, 2 steps are required, 3 steps are required. Okay, and you can pick any one of the problem to get the final solution, and your goal is to here to find out the minimum number of operations. So definitely you will pick the problem which have the minimum solution till that time. Okay, so from this P1 you are getting the minimum number of operation 1. So why you will pick this 2? From this side, if you are adding one more operation, so you will get 2 plus 1 3 here. Oh, here from you are getting 3 plus 1 4, and here you are getting 1 plus 1 2. So definitely your goal is to find out the minimum, so you will always pick the problem which is providing the minimum number of operations if your goal is minimum. Okay, because of that we are just looking the sub problems which have the optimal solution. Optimal solution means what is our main goal is to find out the minimum number of edit distance. Same things we are looking for the sub problems. Minimum, okay, minimum solution what we have till now. So that things we are looking. So these actually every every cells of this matrix is representing the solution of this place. So till now you have 3 ways to come at this position. So either you can come from this side, or this side. 3 side you can come to get the solution. 3 possibility. So you will always choose the minimum value where from you are getting the minimum solution, because final goal is minimum. Why you will pick the maximum?
Yeah. So what is the complexity of this code?
This is also same m into n, because we are simply maintaining 2-dimensional matrix here, where the size of rows is depend on one first matrix, size is of the column is depend on the another matrix. So suppose if length of this first matrix, first string is m, second matrix is n. So that means how many total cells are n into m. Okay, what is the number of rows and columns? So that location you have to fill. Total steps are n into m. So you can see in this code. So this operation, this loop is running only m times. So this is big O m. This loop is running big O of n, and this matrix we are also filling. This is two-dimensional. This is also a big O m into n. Okay, and this part is also m into n. Okay, so these are the four parts we are following inside the loop, and all these actually, what is the maximum among all? This big O m into n. Okay, so finding out the complexity if any operation is performed sequentially, not nested. So in that case, we always pick the maximum. So what is the maximum number of operation part is m into n. So this will become the complexity of this code. Okay, so complexity will be same m into n of the previous added distance, and the LCS, the LCW all have the this m into n. So for this type of problems, what you can do to learn, no need to learn the code, you can just remember this inductive structure and solve one problem manually. Just take some make some matrix on the copy, and just take two strings and fill this matrix by this inductive structure. If you filled one matrix by this inductive structure, you will learn this inductive structure formula, and this is the main part of this solution. So this is the main formula which we generally call inductive structure, and we are using this formula to filling the matrix. If characters are matched, we are looking this value. So this value means this is the sub problem of the previous solution of the previous problem. So we are looking the solution directly and putting at this place. If our characters are not matched, that means we are looking the solution of this part and adding one and storing this place. So this is the things of dynamic. Okay, so we are just looking the solution of sub problems and using the solution and getting the solution of the main problem in this manner. So just look this inductive structure, fill one matrix by manually by paper and pen, and you will just remember all the steps, what are the things we are doing in this added distance or LCS or LCW, and you can write the code. Then try to write the code. No need to remember the code directly. Okay, just remember the inductive structure and fill one matrix, and you can write the code. Okay,
How the problems will be asked, sir, if code is not important and it's only structure is important?
yeah, so this inductive structure actually this inductive structure you can create for any problems. So how you are actually using the solution of sub problems, based on that you can create this inductive structure.
No. What type of problems they will ask?
Actually there are lots of type of problems means where most of the time this type maximum or longest or smallest or minimum, this type of question will be asked, which can be solved using dynamic programming. Okay, and at that time, so every problem is a new, so this inductive structure will change for the according to the problem. So we cannot say that this is the ideal inductive structure you can use anywhere, but this inductive structure used for this problem. So maybe some similar problem can be asked in different ways, so you can use the similar approach. But so because of that, I'm saying that some problems you have to solve to get some idea of the dynamic programming. Okay, so just for this problem which is discussed in this week, just look this inductive structure, okay, and fill this matrix manually by looking this inductive structure. During the filling, you will you have to apply this inductive structure many number of times, and you will you maybe just keep this thing in your mind after just solving one problem manually. Okay, so this inductive structure is very easy because you are filling each position. Okay, so at that time you have to just look that if characters are same, just read the diagonal. If characters are not same, just find out the minimum. So this is very simple approach to remember. Okay, so by just filling all the value, this formula will automatically saved in your mind for this problem. So no need to remember the code for this. So just remember the base case, what base case we are, how we base case we are filling, and how after that how we are filling the remaining cells, and what value we are returning finally. So 3 steps are required: just filling the base case, then filling the cells value, and the formula of the filling cells value is, if the character are same, just read the diagonal. If character are not same, just select the minimum among 3. Okay, for this edit distance. So this formula is changed little bit in the each problem. So all these 3 problem are is approx similar. By just looking inductive structure, very small changes there. So you will get all these 3 problems. Okay, so first fill this matrix manually, then try to write your code by own. So how you are reaching the solution also, you will get this. And last problem is discuss this matrix multiplication in this week. So same things, matrix multiplication, you know that what is this matrix multiplication and how many operations is required when we solve this matrix multiplication. So suppose some example is given. Let me just take some example. This is the matrix. Okay. So matrix multiplication, you can multiply 2 matrix if the size is actually, suppose A matrix is given, B matrix is given, and size of matrix is like 2 into 3. Okay, and next matrix size is 3 into 4, then you can multiply. Okay, so this value should be matched in this order. Okay, 2 into 3, that means 2 row and 3 columns, and this 3 row and 4 columns. If this is the things, then you can multiply this. So during the multiplication, so how many operations are required, how many multiplications operations are required, that we are actually counting here. So how order we can select. So what are the possibility of the multiplication is, suppose we have given multiple many matrix like m1, m2, m3, m4. Okay, so what you can do, and you need to multiply all these 4 matrix. You cannot change the order. Okay, so you cannot just multiply this m1 directly to m3, because this order is given based on this dimension compatibility. Okay, so suppose size is given like 2 into 3 for this, and then 3 into 2 for this, then 2 into 5 for this, and then 5 into 4 this, like this. So order you cannot change. If you multiply this at one time, you can only multiply 2 matrix. So this is the condition of multiplication. If any order is given, so this size compatibility is given, and at a time you can multiply only 2 matrix, either m1, m2, or you can start with m2, m3, or you can start with m3, m4, like this. But there are multiple way to start. Which first 2 matrix you will multiply first, then after getting the solution, then multiply with the second. So suppose if you have this 4 matrix, so what are the possible way to multiply this 4 matrix? So I'm writing the way like this. So suppose first we have only 2, m1, m2. Okay, and you can just assume that size compatibility, you can multiply this. So only one way is possible. You can simply multiply. We have only 2 matrix. We can multiply in the 1 steps. So only 1 step is required here. Suppose if you have 3, m1, m2, m3. Okay. So here order you can change. Order means you can just parenthesize these matrix. Like first, if you multiply this, okay, and after getting the solution of this multiplication m1 and m2, then you will multiply the solution with m3. So that means like this. Okay, So first you are multiplying m1 and m2, and after getting the solution, you are multiplying the solution with m3. Another possible way is like m1, m2, m3. What you can do, you can multiply this first, m2, m3. Okay, and after getting the solution of m2, m3, you are multiplying with m1. So this is the another possibility. So in 3 matrix, only 2 ways of the multiplication. But if we increase the matrix like 4, m1, m2, m3, m4, okay, so there are multiple way you will find out that, like you can just first step you can multiply this first, okay, and this second, and then final. Okay, so first step you can multiply in this manner. So m1, m2, m3, m4, okay, this one and then this one and final 2. Okay, so this is the one way. And second way, like you can perform like this: m1, m2, m3, m4. So first you multiply this, okay, after getting the solution, multiply with the third, and after getting the solution, multiply with the fourth, like this. So this is the another possibility. Similarly, you can just find out the many way. So m2, m3, m2, m3, m4. You can start from the last. Okay, so like this. Okay, then this, and then this. So in this manner, if you figure out that total 5 way are possible for 4 matrix, you can just parenthesize into 5 different manner. So which one is the best order of the multiplication if we are parenthesizing in this manner? So best way means here you will get the different number of multiplications in different way. So suppose I'm taking one example of 3 matrix to better understanding. Okay, so
Sir, I didn't get, like A cross B is not equals to, okay,
sorry,
A, B, C, if three matrices are there, so we can parenthesis any two. Right.
Because at a time we can only multiply 2 matrix. Okay, so you have to first pick 2 matrix in the given order, then you have to multiply them, then you will get one solution for that matrix. Okay, after multiply, then that will also a matrix, then that you will multiply with the remaining one. So I am taking one example for 3 matrix. First thing, what is the multiplication thing, I'm just telling you. So let me just taking one matrix, simple matrix. Okay, so 2 row and 3 columns. So 1 3 column. Okay, so 1 2 3 4 5 6. Okay, so suppose this is the m1. Okay, and m2 I'm taking like 3 row and 2 columns. So like 7 8 9 10 11 12. So this is the second matrix, and m3 is 2 row and 5 column. Okay, I'm taking the another remaining value. So 2 row and 5 columns. So I'm taking here like 1 1 1 1 1 and 1 or 2 2 2, like this. Value can maybe anything. Okay, so 2. So these are 3 matrices I'm taking. First size is 2 by 3, 2 rows and 3 columns. Second size I'm taking 3 by 2, so 3 rows and 2 columns. And third matrix we have 2 by 5, so 2 rows and 5 columns. Okay, now we can multiply this. So if we multiply this m1 and m2, so there are 2 possibility of the multiply. What we can do, we can multiply this m1 and m2 first, and we will get some solution. So in this manner, how you will multiply this m1 and m2? So this 7 9 11, that value will come at this location. So like we will get the solution in this manner. So 1 into 7 plus 2 into 9 plus 3 into 11. Okay, in next, so this is the first. Okay, and same things we will repeat with the second row. So next value we will get this 1 4 into 7 plus 5 into 9 plus 6 into 11. So this is now the first 2 value. Okay, in the final, and similarly we will find out the second remaining 2 value. Let me write here. Okay, So for the remaining part, same things, you will pick this column and we'll just put on this place. So next value you will get this 1 into 8 plus 2 into 10 plus 3 into 12, and next value you will get like 4 into 8 plus 5 into 10 plus 6 into 12. Okay, in this manner you are getting, you will get one value for this position, second for this, and similar for one value for this and one value for this, and finally you will get the one matrix of size 2 by 2. Okay, so let me just I'm not calculating all the values, so you will get like this a1 a2 and b1 b2 like this. Okay, so this a1 is representing this solution, b1 is represent a2 is representing this value, and this b1 is representing this one, and b2 is representing this value. Okay, after multiplication, so what final matrix we are getting? We are getting this matrix 2 by 2 size. Okay, after multiplying this m1 and m2. So how we are getting, so how many number of operation we are performing actually? So you can see that how many multiplication operation we have here. So 1 2 3 4 5 6 7 8 9 10 11 12, 12 multiplication operation we are performing. So that number of operation, how we can calculate directly if we are performing this multiplication. So we can, what we can do, or what size matrix we will get in the output after multiplication. So you can see that after multiplication, this the size of m1 was 2 into 3 and size of m2 was 3 into 2. Okay, because of that we multiply, so we have this size, and finally we will get what is the first value of the first matrix, what is the row, and what are the columns of the second matrix. So that will become a size of the resultant matrix. So suppose if I am giving the name of the resultant matrix like AM, the size will be 2 into 2. Okay, 2 into 2. And what are the number of operation is there? So you can simply take first value, this value you will take one time, and this value. Okay, so 2 into 3 into 2, and you will get 12. So you can calculate the total number of operations are required when you are multiplying two matrices. Okay, so first take the row value of the first matrix, and what are the common value of the column and row of the first and second matrix, and what are the last column value for the second matrix. Just multiply these. So these number of operations are required when you are multiplying these two matrices. Okay, so similar way you can calculate the number of operations. Suppose one matrix size is 5 into 10 and second matrix size is 10 into 2. Okay, this is m1 and this is m2. First tell me what is the size of the output matrix after multiplication, this m1 m2.
5 cross 2.
5 cross 2, yeah, correct. Or what are the multiplications if we multiply this? 5. So first value we will take this, second we will take common this 10, and third we will this take, okay, 2. So these number of operations are required, multiplication operations required, 5 into 50 into 100. 100 multiplications are required if we are multiplying this size matrix. Okay, so in this manner we can directly calculate the number of multiplication operation and what is the resultant matrix size. Now I just telling you what are the difference if we change the order. Okay, so I'm taking this m1 m2 m3. So let me just make here. So size of the first matrix is 2 3 3 2 and 2 5. So 2 into 3 and 3 into 2 and 2 into 5. Okay, so this is m1 m2 m3. Okay, suppose if I just follow this process, so m1 multiply m2 and then multiply with m3. Okay, like this. So this is the one possible order. We are multiplying m1 and m2 first, then we are multiplying with m3. So what are the total number of operations is required if we are following this order? So first m1 and m2 if we are multiplying. So what are the total number of operations? So 2 into 3 into 2, correct? So this is the number of operation if we are multiplying this m1 into m2. You can see that 2, 3 and 2. And after that you will get the one matrix of size 2 into 2. And the remaining matrix m3 size is 2 into 5. Okay, now you have the resultant matrix R matrix and this is m3. So previous number of operation are these one. Okay, and if you multiply this, so you will get 2 into 2 into 5. Okay, so 2 from here, 2 from here and 5 here. So we are getting the final matrix of size 2 into 5. 2 into 5. So how many total operation are required? Just add these. Okay, so this we are getting 2 into 3, 12, and here we are getting 2 into 4, 20. So 12 plus 20, we are getting 32. Correct? If we change the order, suppose if we change the order in different way, so like we have 3 matrix, so 2 into 3 and 3 into 2, same size I am taking, 2 into 5, and m1, m2, m3. Okay, now this time I am just following this m2, m3 first and then m1, like this. Okay, so we are just multiplying this 2 first and then we'll multiplying the resultant with m1. So in this manner, how many we are getting? So you can see that total number of operation is 3 into 2 into 5. Okay, and after that you will get the resultant matrix 3 into 5 size. So 3 into 5. So this is the resultant matrix size, and this is m1 is 2 into 3. And so this is the one operation. Okay, and after that 2 into 3 into 5, this multiplication. Okay, so this is the step, and you will get 2 into 5 resultant matrix final. So what are the operations are required? 3 into 6 and 5, 30. 2 into 3, 6 into 5, 30. Okay, total 60. So if we are changing this order, you can see that previous we are getting 32 multiplication operation total. This time we are getting 60. Okay, so now you can see that. So if there are multiple way to select the order of multiplication, okay, so which order is the efficient order where we are getting the minimum number of multiplication operations? So this is the problem, this matrix multiplication problem. Okay, so that means in this example we have this is the good order to select. Okay, if we multiply first 2 matrix first, then with the third one, so we are getting total 32 operations. If we are selecting the different order, we are getting 60. This is higher than the previous one. So in this manner, if we have 4 matrix, we have 5 possibility. Okay, so out of this 5 possibility, which is the efficient order to get the minimum number of operations? So we are figuring out these things in this problem. So what are the minimum number of operations is required when we are multiplying n matrix? So to solve this, so this is little bit tricky problem. So same things, but dynamic programming approach we are using in this problem. So you can see that how we are filling this. So what we will do, first thing, if you look this things, okay. So this actually is representing the matrix, total matrix, how many matrix we have. Okay, so 0 to n minus 1 and 0 to n minus 1. So this is representing the number of matrix, row and columns. But this things is the repetition of the process, this diagonal things. So no need to fill this part. Okay, we will start filling this matrix from this diagonal position. And why we are filling this? Okay, so you can see. So order. Suppose in this example, if you see, we have this 5 matrix and size of this matrix is given. So M0, M1, M2, M3, M4. This matrix is given. So here actually we are defining this matrix like 0, 1, 2, 3, 4, and 0, 1, 2, 3, 4. So this is the matrix number. Okay, so 0, 1, 2, 3, 4. So what combination we can use? We cannot change the order. Okay, so we cannot change the order like M1 to directly M3 like this. Okay, we can pick only two adjacent matrix when we are multiplying. Okay, after getting the solution, we can multiply with the next. So in this manner, so what this value is representing, so if we have only one matrix, so we are just taking this as a like this 0 and 0. Okay, if we have this matrix, so there is no minimum multiplication operation is there. Okay, so because of that we are filling 0. So this is the sub problem we are taking. We are just considering that we have only one matrix here, M0. So how many multiplication total number of operation is required? Okay, 0, because there is no matrix, no multiplication. Similarly, if we have only one matrix, okay, so suppose if we have only this matrix M1, then still 0 operation is required. Then if we have only M2, 0 operation this. Okay, in this diagonal things, we are only considering that we have only one single matrix in the input, and if we have single matrix, no multiplication operation is required. So because of that we are filling this 0. We cannot fill this lower part because we cannot change the order, because we will always looking for this direction. So because of that, if we are taking two matrix, suppose if we are taking this two matrix in the input, so M0, M1, we are taking now this. So what are the minimum number of operation is required? So that location is just giving this value. Okay,
Sir, the diagonal matrix, 1 and 1. So it is not like we are multiplying 1 with 1.
no, why we are multiplying 1 with 1? Because we are not multiplying the same matrix with the same matrix. Or you can also not multiplying that. If you have matrix, one matrix only M0, and size of this is 4 into 10. Okay, so how you can multiply with the same matrix? Because the size of this same matrix is M0 4 by 10. But for multiplying the matrix, you should have the same number of rows and same number of columns with the second. Then you can multiply. Okay, and here our goal is not to multiply with the same matrix. We want to multiply all the matrix, not with the same.
Okay, sir.
If suppose if this problem is given and M0 is given, and you are asking that what are the minimum number of multiplication operation is required, you have only one matrix, there is no matrix, so this is the output. 0 multiplication operation is required. Because of that we are filling directly 0. Okay, similarly if you have given only M1, then you have only 0 operation required. So this diagonal things is representing that if you have only single matrix.
And sir, this 1 and 3, why this is 0?
Where 1 and 3?
3 row and 1 column.
This one, because we are not interested in this side direction, because we can get the solution, so we will always multiplying in this order, no?
Okay, in
So
this order.
this
okay.
order, so
Fine.
M0 and 1. So because of that, if we are taking these things 0 and 1, then we have two matrix now, then we can multiplying this 0 to 1.
Yes, I got it.
Okay, so we can get the solution only by filling this diagonal part. No need to fill this, we can start from this diagonal thing. So now we will increase the problem size. Initially we are just assuming we have only one, then we are filling 0. Now we will increase our size. Now when we are just considering, we are looking for this position. Okay, so that means we have now two matrix, M0 and M1. Okay, now what are the solution if we have two matrix? So in this case, what we will do, we will directly just multiplying the things, because we have two matrix, we can calculate the direct number of operation by this size. So simply 4 into 10 into 3. So 4 into 10, 40 into 3, 120. So we are getting the solution if you have two matrix. Okay, so only this location is there. Now we have the solution for this 2 matrix, and this solution is the optimal solution because we have only 2 matrix. There is no other possibility of the order. So this 120 is representing the optimal solution. Similar for this position. Okay, so for this position, that means you have this okay, 1 second, 2, this 0 and 2, no, this 1 and 2. Okay, so that means you have the possibility of, you have 2 matrix only, M1 and M2. Okay, so if you have M1 and M2 only, so this location is representing 1 and 2. So that means you have only 2 matrix, 1 and 2. So what is the solution? So 1 to 2. So 1 to 2, only one solution is possible. You can simply multiply this. So 10 into 3 into 12. Okay, so this operation is required, total 360. So you can directly fill this in this manner. Okay, similarly for 2 and 3, so this value is represented. So this matrix we will fill diagonally. Okay, so like first diagonal things we filled by 0, next diagonal we will fill. So in this manner we will fill this matrix. So in this next things, M2 and M3, so both are the continuous matrix, 2 matrix. So in this manner you will get what is the size of this M2. So just multiplying this 3 into 12 into 20. So you will get this 720. Okay, next location, this one 4 and this 3 and 4. That means you have only this part. What is the best solution for this M3 to M4 multiplication? So these are the continuous. You can multiply these 2 matrices in only one order. So if you just check that 12 into 20 into 7. So 12 into 20 into 7. So you will get on this 1680. Okay, so in this manner we are filling this matrix. So this row is filled now by the simple steps. Now we will fill this first. Okay, so now this location is now you can see here, this is 0 and this is 2, 0 to 2. Then that means you have matrix M0, M1 and M2, and we are finding out the minimum number of operation. So in this case you have multiple orders, so you have some solution also here. So what you can do, M0, M1 you can multiply first, and then you can multiply with this M2. Another solution, you have M1 and M2, you can multiply first and then with M0. So 2 order are possible in this case. So we will figure out this, which one is the best. So for this case, and for this, or you can directly read the solution of the previous problem. So when you are multiplying this M0 with M1, you have already solved this problem, and you can directly read the solution from this value 120. Okay, so 120 you can directly read because this M0 and M1 we have already solved. And what is the resultant side of this M0 and M1 is, so we can directly figure out this 4 into 3. So 4 into 3. And what are the next matrix? We have M2. So M2 matrix size is 3 into 12. So 3 into 12. So this solution we will directly read from the matrix which we have already solved, plus what we are getting new. So 4 into 3 into 10. Okay, so this is 12 and 120. And okay, I think something is wrong. Sorry, 12. Okay, so this is 12. Okay, so 4 into 3 into 12. So 12 into 12 is 144, and 144 plus 120 is 264. Okay, so this is the one possible. We are getting 264 from this. We have another choice. So this time we can M1 and M2. You can see that M1, M2 we have already solved in this problem. So M1 and 2, this part we have already solved. So we will directly read this output 360 here. And after getting, what matrix size we have is this 1 and 2. Okay, so 1 and 2, 10 into 12. So 10 into 12, this is the output size, and M0 size is 4 into 10. So 4 into 10. So we will get 4 into 10 into 12. So this is like 120, and 240, 480. So for this we are getting 480, and from previous we are getting 264. Which one is the minimum? 264. That we are filling at this position. Okay, so you can see here how we are using the previous solution from our matrix. Okay, so some part we have already solved, so we will directly look the answer from the matrix which we have already solved. The remaining part we will calculate, and then we will pick the minimum among all. So same things we will perform with every index. So this part we have get same from this position. So this position is 1, 2, 3. So that means we are picking this order. So M1, M2, M3. So M1, M2, M3. Okay. So if we are picking this, so we can either choose this M1, M2 first, and we have already solved this solution in this matrix. So M1 and this M2. So this solution is representing 360 here. And then we will add this value with this part. Another solution is M1 into M2 into M3, like this. Okay, so M2, M3 we have already solved. M2 and M3, you can see that we can directly read this value. And which one we are getting minimum, we will fill here. So in this manner, we will fill this matrix. Every time we will check what value we have already calculated, we will directly read the solution, and we will select the minimum to fill. So this part will be filled. Similar way, we will fill these things. In the all possibility, we will select the minimum, and we will fill here. And finally, we will get this. And this is representing the minimum number of operations required. So this approach we are using to fill this matrix. If you see the inductive structure, so this is the inductive structure for given this. So this is the base case. If I equal to j, if both are same, then we are filling 0. So this is the diagonal things. Okay, if I and j both are same, we are filling 0. This diagonal. If both are name same, not same, then we are picking the minimum value, and this formula is actually calculating the all possible way of the order of the order selection. Okay, and you can see that CIK, this value we are directly reading from the matrix. This value we are directly reading from the matrix. Okay, because C is the matrix name, and we are adding the additional things. Okay, so which size we are multiplying with the single matrix, what are the number of operations is required. So, and k value, you can see that for k value is starting from I to less than j. So this k value is actually defining all possible order. So actually if we have 3 matrix, so we have 2 order. So this k value range, if we are taking k equal to I, then 1 order we are getting. If k value we are increasing next, so then we are getting the second possible order. So this k loop, this for loop is actually deciding all possible order, but every time we are reading the previous solution and adding the new, which we are just multiplying. Okay, so we are not calculating the all possible solution again. If we have already solved, we are directly picking from the matrix, so this location, and adding the next solution, and out of these we are picking the minimum. Okay, and filling. So in this manner we are filling this matrix. So same things we are doing here. So finding first things, we are just maintaining one KL list, and we are calculating the solution for all possible order for this size, and after that we are just returning this minimum of all the possible solution. Okay, and filling this location, and finally we are getting this C0 and n-1, the top location, this value, and this value is representing the minimum number of operations required to multiply the matrix. So in this manner we are getting the minimum number of operations. So but how we can achieve the what order we should follow? Okay, what order we should follow to getting this solution? So that things we can achieve if we maintain the k value. Okay, so this k value is just representing the order of multiplication. If like we have 0, m0, m1 and m2, if we are taking k equal to 1, so that means first bracket we are putting here. Okay, and we are solving this first and then multiplying with this m2. Okay, if k value is like 0, so k value is equal to 0, that means we are just looking this m0, m1 m2. That means this bracket we're putting here, and we will first solve this and then this with this one. So based on this k value, for which k value we are getting the minimum number of multiplications, so that we will just maintain in our record. So based on that, we can just parenthesize in the output. So you can see that for the same example, now this time for which k value we are getting this 120. So we will just read this information, store this information in our matrix or in some place. So 0 value. Okay. So in the inductive structure, you can see this k loop now. This one. Okay. This k value. For which value of k we are getting the minimum number of operation. So we are storing that value in this. So here for k equal to 1, we are getting this minimum value. Okay. So in this manner, we will just store this k value with the value, and after getting the solution, so we have 4 matrix. So how we can achieve the order of parentheses? So we have m0, m1, m2, m3. So we have 4 matrix. So we will just look the final value. So this is the minimum number of operation to multiplying all the matrix m0 to m3. So just we will look this what k value we are getting at this place final. Okay, so 1. So first parenthesize we will just put here like this. Okay, 1 by reading this value. Now you can see that inside this parenthesis we have 3 matrix. So then we have to figure out the solution for this part, which order we have to follow first with 1 to 3, because this is the fixed one. Okay, after getting the solution of this m1 to m3 multiplication, we will multiply with this m0. But inside this m1, m2, m3, this is multiple order. So how we will figure out this? So just look the value of 1 and 3. So this is 0, 1, 2, 3, 4 and 0, 1, 2, 3, 4. So 1 and 3. Okay, so this is the value next. Okay. I think something. Oh, we have 5 matrix. Oh, I missed something. We have 5 matrix total. So m0, m1, m2, m3, m4. So first we have actually 1. So we will parenthesize this here. Okay, now we have 1 to 4. So 1 to 4, we have this value. 1 to 4, yeah, we have this value. Let me check again. So initially we have matrix m0 to another 2 matrix set can I multiply. We will check the C0 to 4. So the first parenthesis is okay. I'm just marking the incorrect order. So based on this 1 value, so this is the closing parenthesis we will put here actually. So if we are taking this m0, let me just remove this. So first value we are getting 1 here. So first we will mark it this 1. Okay. So we will get 2 partition here after marking this 1, because we are getting from the what is the k value for 0 to 4. So and we are getting 1. So we will just put this first parenthesis. And after that, so this is the 2 matrix. We will simply multiply. We cannot change the order, but here we have 3 matrix. So 2 and 4. So what is the value for the k for 2 to 4? So 2 is here and 4 is here. So 3, you can see that we are getting k value equal to 3. So second parenthesis we will put here. Okay. Now you can see that all matrix are, there's no way to change the order here. Okay. So first we will multiply this one, and you can multiply with this separately, and then you will multiply the solution with this one, and then final solution with this one. So this is the order of parenthesis, where if you follow this order, you will get this 13, 4, 4 multiplication, which is minimum. So this is one matrix multiplication problem which is discussed in this week 9. Okay, so just take one example and just follow this inductive structure and fill this. one table, you will get how this code is working, and we are following this inductive structure and how we are calculating. So this inductive structure is working in the similar way which I have just discussed in this example. Okay, how we are filling this matrix. Okay, any query? So this is the last topic of week 9. So after that, just solve all the practice problem, graded problem, and live coding problem. Okay, so you will get more idea. So after 5 in the assignment and 4 in the live coding, so 8 more problem. Okay, if anyone have any query?
Such long sessions have less productive effects. I think you really get into a mental fatigue. Your absorption rate goes down. I don't think it is worth to really stretch the course beyond 2 hours.
Yeah, but okay, so just try your own. Okay, if you are facing difficulty at any point, just watch the.
No. What I'm telling is, I think you should balance the. Because it's lost to for half an hour. It's almost confused totally.
Your content is actually thoda heavy in this course.
Okay, so.
Okay. So next week we will conduct revision session for the quiz. Okay, so maybe both session will be scheduled for the quiz.
And week 9 we have to submit also, no?
Yeah, week 9 you have to complete.
So we are not going to discuss that.
Yeah, in next Friday is actually live coding. You can also discuss some things in the live coding session which is related to the week 9. But in the next week, which is actually we want to conduct 2 revision session for quiz 2.
Yeah.
Okay, and for the 2 week each. So maybe you will discuss all the content from week 5 to 8 in that session. Later we can discuss. Okay, so after the quiz we will discuss the things again. If you are facing difficulty in week 9 content, then we will discuss again.
No, but submission is happening before the quiz, no?
That submission deadline is I think before the quiz 3. So you can, if you have any problem, you can discuss on the Friday session then.
All right.
Okay, and I think the TA session is also on Thursday. So tomorrow you can also discuss some things required.
It's all piled up together now.
Okay.
Okay. Thank you, sir. Thank you very much. Good night.
Okay. Good night, everyone.